Welcome everyone. We have celebrate the solstice at IFISC. In summer we go to the beach, and in winter we try to do something a little bit more professional. So we started last year with the idea of having very short talks that try to summarize the work done during the year. And we continue this year with these 5 minutes Ignite talks. Let me make clear that those are talks about papers that have been published during this year by members of IFISC. They are not selected as the best papers of the year, but as representative of the different types of things that are going on in the institute. I will not try to summarize what we have done in this year. For that, I need your help, and all of you have received a message this morning, so please answer to that message and read it and give the information, and from there we will be able to make the annual report of the year. Now, this is the order of the talks. I've seen that last year they were ordered alphabetically. That made us more, but this year these are in the order of our research line. So we have one by Raul on the general line, David and Roberta quantum, Ingo nonlinear photonics, Emilio fluid dynamics, Tobias and Claudio on bio things, and Jose and Damian on socio things. So let's get started, and I will be strict with the 5 minutes. So first, first Raul.
Este es el... Siempre, there will always be a free chair. But the music chair that we need to turn around. So the music sounds and then we stop. Okay, this is a work I did with Karel Porsmans and Christian van den Broek, who sadly passed away a few months ago, so I would like to dedicate this presentation to him. It's a rather technical thing, but I think it's also very interesting, rather than technical. It's these phase transitions in persistent and random tumble walks. So what is a random walk? You all know the idea of this random walk, in which something like a trunk moves randomly. In the usual random walks, the movements are completely random because they are mediated by the interaction with the environment. Okay, so there is no internal dynamics of the walker. So this is the person completely drunk, so he moves away in a completely random way. This is the case of Brownian motion discovered by Brown a few 200 years ago. Now, in other cases, you have that the particle has a dynamics of its own. It's called an active particle. So it's not just, of course, the movement is still random, but there is some inertia in the movement. Okay, it's not just mediated by the fluctuation, not mediated by the environment. There's also some internal dynamics, and this has been used to model the movement of bacteria, birds, fish, quadrupeds, cars. You have seen all these nice movements, which, of course, on top of the random dynamics, there is some internal dynamics. One version of the random walk that considers this inertia is the persistent random walk, introduced almost 100 years ago, supported in mathematics. What you have is a random walk in which the tendency to continue in the same direction is greater than the tendency to change. There is a particular version which is called the run-and-tumble, in which there is a constant rate. So the particle moves, and then at a constant rate it switches direction. Okay, this is a typical trajectory of a persistent random walk. So once you have these models, you can, for instance, quantify which is the probability that the walker has reached a given position. In the usual random walk, it's very easy to do. You all have done this exercise some moment in your studies. So you simply define the position of this can walk right or left with some probabilities. You can define the position, and then you compute the probability, which is a binomial distribution. This binomial distribution admits a large deviation form. That's the thing I want to stress. So in the limit of n large, this probability can be written in this form. It's a constant which depends on n, and then the exponential of minus n, which is the number of steps, times a function of the intensive variable x, which is the total distance. Okay? And now this large deviation, in that case you can compute, is this, and it has this particular shape. Okay? Nothing very, very interesting. And this is what you get. This is the Gaussian approximation that you have to see. Now, what we've done is the following. We have, whoa, okay, that should not be there. Okay. We have, of course, here you can see that it is very unlikely that you have a large movement to the right. You move randomly. After n steps, it's very unlikely you have reached n steps to the right. Okay, these are very unlikely events. Unlikely events, but have no zero probability. How can you force those unlikely events? You can pull. You can put a preferred direction, introduce a bias in the movement. So you can explore the region of rare events by adding a force. How do you relate the force with this large fluctuation function? That's what we have done. We have seen that the force, the response to a force, is given by the derivative of the large deviation function. The details do not matter at this stage. Okay? But how you react to a force is related to the large deviation. And then we have compute for this run-and-tumble works. We have compute the response to a force. And this is for the random walk, for the usual random walk. There is nothing, I mean, this is the response in 1 dimension, 2 dimensions, 3 dimensions, infinite dimensions. And you can see which is something very uninteresting. I mean, the more you pull, the larger is your, the more you pull, the larger is your deviation. Good. But when you do the same thing for these run-and-tumble walks, you find something which is rather interesting. Is that there is a phase transition. So you pull, and after pulling of a certain intensity, you reach the maximum extension. There's a discontinuity in this case. This discontinuity that has been proven mathematically, this all theoretical work, can be related to a condensation in the ground state, which is similar to a Bose-Einstein condensation. Okay, so we have found this similarity between the Bose-Einstein condensation and the force extension versus force relation in a persistent random walk. More details. I'm here almost 24 hours a day. I'm sorry.
Okay, so the title is Nonlinear Chiral Refrigerators, and this was work done in collaboration with Rafael Sanchez from the Universidad Autónoma de Madrid. Some people in the quantum transport community think that we are brothers, but it's not the case, as far as I know. And then Rosa, you know, and Björn Soderman from Duisburg Essen in Germany. So, yeah, so one of the problems in nanoelectronics is how to decrease heat dissipation, right? Because when you integrate many different nano devices, then heat, you produce a lot of heat. So one possibility is to use thermoelectricity, right? Because with a thermoelectric module, you don't have only a heat engine, okay, between, you can, let's say, convert heat into electricity, but also you can cool a system, okay, by, let's say, applying a current, an electric current through one of these thermoelectric devices, you can actually cool an object. In nanoelectronics, in the last few years, there have been kind of excitement because people demonstrated that when you use multiple terminals, then you can increase the efficiency of these cooling devices. But of course, you don't need only to increase efficiency, but you also have to increase the power, okay? The amount of heat that you are able to extract from the object that you want to cool, right? And to do so, then it is necessary to break transversal symmetry, for instance, with magnetic field. So we here in this proposal, we combine these two ingredients, namely the 3 terminals, okay? So here our device operate between these current terminals, between terminal 1 and terminal 2, and this is a heat terminal. And here, this is where we extract the heat, so we are trying to cool this device, and this acting as a voltage probe. So you can actually separate the current, the electric current, and the heat current, okay? And that increases the efficiency. You break time reversal symmetry by applying a magnetic field, so you go into the quantum Hall regime. So in this case, electrons form these chiral states, okay? Here, this is a quantum dot, this is another quantum dot. So electrons, let's say, move along these yellow regions, but due to chirality, it is possible to extract heat from terminal 3. So this is, let's say, very schematically the, let's say, working principle of our device. So what you do basically is you're occupying cold states with electrons, and then you are extracting let's say, hot electrons from terminal 3, okay? So to do so, you have to tune the electronic levels of dot L and dot R in a proper way, okay? And this is, let's say I can show you some results. Here, for instance, we calculate the coefficient of performance for this refrigerator, which is defined, as you know, as the heat extracted divided by the power that we inject into the system. And then if the resonance, the width of the resonance is small, the coefficient of performance increases. Okay, and this is because this let's say device works as an energy filter. Okay, the problem, of course, is that the power that you generate is small, so you have to combine this with an increase of the temperature, of the base temperature of the device. We also calculated, as a function of the applied voltage, the minimum temperature that you can actually reach with this device, okay? And then we estimate that for a device which is at a background temperature 150 millikelvin, you can actually reduce further down to minus, this amount, minus 60 millikelvin, okay? And that's all. Thank you for your attention.
No, I timer. No timer. just do like this. Thank you. Okay, so today I will present this, and notice that it was actually submitted, as Alberto was reminding me yesterday, New Year's Eve. He was submitting the paper, but there was a good end at the end. So this is synchronization in dimer lattices, and the idea is to explore synchronization in these quantum systems. Classical synchronization is well known from the 17th century. I don't think it needs to be introduced here, but just to know that lately there have been some work also to generalize this phenomenon into the quantum regime, and we had a couple of book chapters on this topic. So our first work was actually some years ago, and in that case we started to put the base of something that we've been using also lately. That is the fact that we call quantum synchronization something that you can observe when you look at the local observables. So you have a quantum system, but you can still look at local observables and define the synchronization between these trajectories, and then look at the correlation as you would usually do in a classical system, for instance, with the time correlation with the Pearson factor. And then another thing that is important in this work is that we established that the presence of collective dissipation can introduce a separation in the time scale of dissipation and then give rise to synchronization. So building on this, we have explored several systems. Among them, for instance, an example in optomechanical system, you can have that this dissipative coupling introduced by collective dissipation is enough to lead to the system to synchronize, even in absence of a coherent coupling. And more recently, there have been works exploring synchronization in presence of collective dissipation, even in atomic systems. So for instance, here in this team of Holland, they were considering two atomic clouds in a cavity, and then this collective dissipation can give rise to synchronization between the two clouds that are detuned, okay? And there have been some preliminary experimental results. We were looking also at the relation with synchronization. But now our aim in this last work was to see, okay, is necessary to have collective dissipation? Can you have synchronization if you have separate but dissipation? And then building on the proposal that was given by Schwager, Sirac, and Gittke, in which they were actually showing that you can create with an atomic lattice a dissipative Ising model. So using their proposal, we modified their proposal considering that the lattice that is trapping the atoms is actually dimeric, is actually bichromatic, so you can actually have a trap that is modulated. And in this case, you can actually look at the lattice in which you have your spins that are coupled, but you have modulation both in the frequency and in the losses. So in this situation, what we found is that actually the presence of this imbalance between the losses, so you have the Ising model and the losses are modulated. If you have imbalance, you can have synchronization. And in absence of imbalance, you don't have it. So for instance, this would be in time, the quality of synchronization when you don't have an imbalance, and you see that is not reaching the maximum value 1, so you don't have synchronization. But in presence of imbalance, you can synchronize the system. And let's keep this. So the main message of the paper is that the presence of these staggered losses can introduce synchronization. The things, if you want more detail in the paper, there are analytical calculations because you can actually look at predict the synchronization, looking at the eigenvalues of the Liouvillean that is describing the dynamics of this open quantum system. And then we have identified, looking at the parameter region, two regions, two kinds of synchronization, let's say. One is this intraband synchronization, and the other is interband synchronization. In this regime, you have several modes into the system separated by their energy and with gap in their losses rate. And the slowest mode is the one that determines synchronization. This is what happened in this parameter region. These are the tuning and coupling between the spins. But there is also another region in which you actually have two bands of modes, and you have a kind of two-body behavior. And also in that regime, you can have synchronization. I think it's enough. 5 minutes. This is gone. A reminder for the senior to send the things for the Tematica of CSIC.
I thought you always should start with a bit of a surprise. So every one of you will be familiar with the concept of weather and climate, and that there are different quantities. In particular, these days you will be familiar with that. So weather is something related to short-term prediction of certain variables like temperature, precipitation for the next days. And climate certainly is the property of long-term statistical properties. You might not be so familiar with that the concept of climate and weather can also be extended to dynamical systems. And that is something that already Floris Takens, mathematician from Groningen in the Netherlands, introduced in the mid-90s, where he said, okay, in a dynamical systems you might also have different intentions to either, for example, have a short-term prediction, for example, of a chaotic time series, or you may want to compare the attractors of these systems with each other, which again are rather long-term statistical properties. So this would be referred to one time step ahead prediction as weather forecast, and the chaotic attractor would rather refer to the climatic properties of a dynamical system. So the question we were actually asking and following and trying to answer is, how can we realize a dynamical system that can reproduce the climate of a dynamical system? And actually, even if we don't even know the equations that are generating this dynamic, so this can be a black box and produces some kind of dynamical behavior. So how can we realize one or more of these kind of replica systems which we can train to show the same kind of climate, dynamical climate than the black box is generated here? And for time series prediction to start with, so weather forecast, there are solutions. For example, reservoir computing has been shown in simulations and in experiments in hardware implementations to be excellent in time series prediction. I will not introduce reservoir computing here because you had several talks this year which introduced the concept quite nicely, and you can always go to the very nice video that Irene created on our YouTube channel. But so the step one that we have to do here is we have to realize a system that can do very good time series prediction. That's the reservoir computing. So we will get always a driven response of the system. So it's driven by the black box dynamics, and as output we can get a prediction which hopefully coincides with the original one. Step two would then be we get rid of the drive and instead close the loop, so the predicted value is being fed back into the input of the reservoir computing, and then we will get an autonomous oscillator. And hopefully the autonomous oscillator will realize the same kind of dynamics than the black box. But that's not trivial, because remember, climate and weather. When you have a very good weather forecast model, doesn't mean you will have a very good climate model. So the question is certainly, will this indeed actually lead to a very good climate reproduction? So does good short-term weather prediction imply good long-term prediction? And the question is no. Not surprisingly, if you're familiar with weather and climate, because, for example, this is simulations from Ed Ott's group. If you here have the parameters of a reservoir computer, which does very well in time series prediction, you get more or less the same kind of dynamics, and under similar parameters and similar quality of prediction. Here you see the red curve is the one of our reproductive system, a reproduced system, and the blue was the original. They end up on completely different attractors and show completely different dynamics. And the same happens in our experiments with a hardware reservoir computer. You can either get, we fed, for example, a Rössler attractor, you can either get a nice Rössler attractor, or you may, after some time, end up again on a completely different attractor, which here is a fixed point. So our assumption was transfer stability properties of the attractor are not well reproduced in this case. And how can we overcome that? We can overcome that by adding, for example, some Gaussian noise to the input during the training phase. And you already can see by eye that when this is the original and this is the reproduced system without any noise added, that there are some fine structures here from the Rössler attractor, which if we add this 3% of input noise, we get a better reproduction of the fine structure. But certainly, this is only by visual inspection, which is a little bit unsatisfactory. So how do you quantify that? How can you quantify the match of the climate of different dynamical systems? So how do you compare the chaotic attractors with each other? What we did, in order to quantify that, we either compare the or calculate the cross correlation of the fluctuation spectrums, or use recurrence analysis, which is very common in dynamical systems theory, and where you can find, for example, very nice review about it here. And indeed, we find that with a little bit of noise, we can get better results than without any noise. And you can think about that the noise is actually perturbing the system in the transverse manifold or transverse to the chaotic attractor. And so you train actually the stability properties that otherwise are not included. What are the possible applications? Anything that is related to replication of climate over complex dynamics. For example, you may try to decrypt chaos-encoded messages. But also, it might be interesting for testing the sensitivity and robustness of real-world dynamical systems that you can measure, for example, certain ecosystems, but on which you don't want to hamper with. So don't do then the experiments on the real system, test the copy. And then you can, for example, see whether there are some tipping points and stuff like that, and robustness that you have to consider. That's this paper. And if you have further questions, ask my smart co-workers, Irene or Miguel. Thank you very much.
This is a paper done with Gabor, Cristobal, and also it's part of the thesis of Pedro Monroy. It's published in Journal of Geophysical Research. So what is this about? It's about motion of particles in fluids. So there is a fact that this water in oceans can be considered a very incompressible liquid. This means that if you have some blob of fluid and it moves away, typically if you elongate it in one given direction, this should be accompanied by compression in other directions because the volume should be conserved because the flow is incompressible. As a consequence, you can show that if a region of fluid initially is initially uniform in density, in time it will remain uniform in density because there is contraction. You compress it in one direction, but you expand it in another one. Okay, in oceans there are many studies of a problem, of the sedimentation problem. This is very important to understand the carbon pump in how carbon leaves the atmosphere and goes to the deep ocean, and there are instruments called sediment traps to look at the sedimentation of particles. And it has been observed that in this sedimentation process that you can find very inhomogeneous readings if you put the sediment trap here, or say 100 meters to the right or to the left. So the distribution of the rain of particles that fall into the ocean is very inhomogeneous. It's very different as a function of space. This is usually attributed to an inhomogeneity in the sources. So it means that in the upper layer of the ocean there are particles produced in a large quantity here and in a small quantity here. This is why the instruments below measure different things. But this is not really okay. This has been questioned in some cases, and it happens that there are other works saying that the difference or the inhomogeneities in the bottom are due to particle inertia. It happens that if the particle doesn't follow exactly the motion of the fluid, has some mass, and it's heavy than the water or lighter than water, it will follow slightly different trajectories that can explain some clustering. So this is a simulation in turbulence in which you see clustering of particles in a situation in which if the particles have no inertia, have the same mass of the fluid and zero size, the distribution, an homogeneous distribution will forever remain homogeneous. But we have some other work in which we show that for particles of this type, biogenically originated particles, so plankton bodies or fecal pellets, or this kind of particles that are the ones that are of interest for the sediment traps, the effect of inertia is completely negligible. So one has to look for other explanations, and we found something which is it's quite obvious, but one has to look at it, is that I tell in the first slide, or the second slide, I tell you that as a consequence of the incompressibility of water, a region of fluid initially uniform in density will reform uniform in density. This is true in 3D. I mean, a three-dimensional region of fluid will remain with uniform density in 3 dimensions. But if you release the particles only in a two-dimensional, the surface of the ocean, this is no longer true. And this is an example. This is a simple simulation of how a sheet of particles falls in turbulence. And you see it falls, and then when it reaches the bottom of a container, the distribution is no longer homogeneous. And the reason is that this is not a contradiction with the statement. If you put a three-dimensional blob, this three-dimensional blob will remain homogeneous all the time, but this is not the same if you project this into dimensions. In fact, there are two effects. One is that the sheet can elongate more in two directions and compression in the other, so in this direction the density will be changed. And also when it falls into the bottom, there will be a projection effect. Both effects cooperate, and we have studied this in a particular setup. This is the south west coast of Africa, Benguela region. We have studied this. It's a quite interesting region. We have used velocity flows there and studied the release of particles from the top and how do they reach the bottom. Well, a layer, not exactly the bottom, a layer at 1 kilometer deep. And okay, and also we have developed a theory. It's a geometrical theory. So we're trying to explain what will be the inhomogeneities in the bottom. So you have a surface that is falling. There will be two effects. On the one hand, the flow will elongate, will change the shape in this area of this surface, and also when it gets to the bottom, the footprint that is left will be, so there is a projection effect that will change this area. You can do some mathematics and obtain expressions for the density at the bottom in terms of the density up and the fluid during the trajectory. And those are the results. Those are the numerical simulations of release of particles for several falling velocities, different falling velocities, and this is the result of the computations from this theory, from the formulas of this theory, which are in good agreement. It's a final thing. In the numerical simulations, you can find large inhomogeneities, even strongly places where the density is really high. We can explain this. Is what in mathematics can be called caustics. You have a surface falling, you will have the surface, the density here will be related to this area, but if the density, this falls in this way, you see the area is much smaller, so the density will be much higher. We can relate this effect. So here the density will be very high, here the density will be low, and is related to the projection factor, one of the two factors that deal with the dynamics of this process. So, and finally, I finished. Certainly the position of particles in the ocean is inhomogeneous. This is just plankton seen from space. The position of in the area of Benguela, the position of particles from this layer will be more or less related to the density of planktons seen from space. And this is our geometrical computation. If you release homogeneously in this region the particles, at the bottom this will be the structure found. You can combine both to obtain a prediction of what will be the density of particles at the bottom of the oceans because of the two factors that can be useful to understand the relationships with experiments on sediments. That's it. Thanks.
So I'll continue. So I'm not going to talk about what is life, but how does life form, okay? So this is a part of a contribution to that question, an answer to this question. So it's a long title, and there's not enough time to explain in detail what all these words mean. But broadly speaking, it's about formation of embryonic structures. So this is an embryo of a zebrafish, and it forms these what's called somites. They actually, in the end, give rise to vertebrae, for example. And the mechanism by which this forms, or it's thought to form, is the so-called clock wavefront mechanism. So there's a model for that. And I quote these pictures are from this review by Saúl Ares and others. And this works roughly like this. So I hope this plays. So there's an oscillation going on, this blue thing. And then there's a wavefront traveling in the embryo. And whenever that wavefront hits a certain phase of that oscillation, sort of a segment forms, if you like. So that is I'll go back and play it again. So you see this front moves and you have this background oscillation. And what is oscillating there is the gene expression or the expression of certain genes. And this blue part is made up of many, many cells. And so what you need in order for this to work is that these cells must have the same frequency in oscillation. They must be in phase, this must be coherent, and must have a sufficient amplitude. And so these are sort of oscillations within cells. Different cells are different, they have different shapes and different things. So you must guarantee these things. And in this paper, we sort of investigate the effects of noise on processes like this. And the process in detail involves genetic transcription and translation and what's called delta notch signaling between neighboring cells. If you want to know more about this, you have to read the paper or come to talk to me. But broadly speaking, when the cells are not coupled, they don't synchronize, and when they are coupled, they can synchronize. don't have to, but they can. And the effect of noise is very important in there. And one source of noise is the fact that the number of molecules in these cells that contribute to this is very small. And so this is from a different paper that I did a few years ago with, well, I was on it, with people in Manchester, with experimentalists. So they show you these pictures of cells, and each dot here is a messenger RNA molecule, right? So when I first saw these pictures, you were sort of amazed, right? So, or if you're not excited by this, then you don't like science, right? I would say. So, and they count them in the very small numbers, right? So this is far away from the thermodynamic limit, and then reactions are stochastic, and you need to model this accordingly. And that's what we did in this paper, and this is a stochastic interacting particle model with delay, and then you study this with methods from statistical mechanics, so path integrals, small noise approximations. You look at pattern formation in waves, and you simulate it with modified Gillespie algorithms. This is all stuff that you learn, for example, in the master's course here. Then you see these synchronized, so this is sort of position and this is time, so you can see these sort of synchronized oscillations here. You can characterize this analytically, so you can compute the peak frequency, the frequencies with which they oscillate and that they align, and when they align with increasing coupling strength. You can look at things like phase differences and so on. You can also show that the amplitude of these oscillations increases as you increase the coupling strength. So this has to do with a phenomenon that is called amplification of intrinsic noise. You can also show that the coherence goes up. So these are all outputs of that path integral approach, if you like. And you can also show that these things can sometimes oscillate in phase and out of phase. So there's also arrangements where neighboring cells sort of oscillate out of phase. And this depends on, there's several different types of delay, and sort of white and black here indicate in phase or out of phase oscillation. So in that, certain combinations cannot can be such that this biological system would not work. That is not useful for the biological function. And you can also induce traveling waves and so on by certain combinations of the delays, for example. So to the master students, I say, and I use this shamelessly, right? This opportunity. If you want to know more about this, what is life, right? Then you should take this module in semester 2, right? So, and this is taught by Manuel and by me. These pictures were taken this morning. We'll talk about some of these topics, right? So there's a long list that you can find online, but it's about biological networks and noise and so on. Sorry? This is the commercials break, exactly. So come to this course if you want to know about this, right? And there may also be master's projects in this general area. That's it.
Well, good morning, everybody. The paper I'm going to talk about is one I published with a group of Brazil that I have been collaborating for some years, a group of Mauro Copelli, but also there is Ana Alonso, who was a former master student here. This paper for me is interesting because it's important, for it's a kind of culmination of a study that started about more than 15 years ago, when Raul Toral and I discovered a paper by Henning Bosch, where he proposed or discovered a new synchronization scheme, what he called anticipated synchronization, in which a system which is receiving information can predict the dynamics of the sender. So the idea is you have two coupled systems. Two coupled systems, X and Y, and if you suggest the Y to a delay feedback, a negative delay feedback, this system can predict what the system is going to do in the future. And he proved it analytically, mathematically, there were some experiments and so on. So when we found that, Raul and I started to study these systems in non-autonomous case. Actually, we took two excitable systems, forces system, and showed that in a certain parameter value for the coupling and the delay, still anticipated synchronization can be observed, although it is not a solution of the system, but the system tends to operate in a regime where the receiver predicts what the master is going to do in the future. 1 year later, Raul and Salvador and Marcena, which was our PhD student, proposed a mechanism for which this happened. They say that the delay feedback produces a reduction of the threshold, excitability threshold in the slave system. As a consequence, the response is not the same for the two systems, and this allows to explain a simple mechanism that produces anticipated synchronization. Well, let's see if that's all. A few years later, with my colleague Mauro Copelli, we thought that we should try to see if this is relevant also for the brain. So we started to translate the Voss scheme into a neuronal scheme in which instead of having only two systems, we have a sender and receiver, which might be a neuron, a population of neurons, or whatever, which is subjected to an excitatory coupling, and then I have, instead of the feedback, I put an interneuron, which produces an inhibitory coupling, which makes a kind of inhibitory feedback into the receiver neuron. With this model, we proved that you can have a transition from delay synchronization, where this follow this, to anticipated synchronization, where this react before this one. And actually, what is interesting is not only that the inhibition has to be changed, but also the ratio or the balance between excitation and inhibition can be changing, and you can have delay synchronization or anticipated synchronization in neuronal systems. With that, we demonstrated, or we showed that, or give rise to some experimental data from a group in the United States where they found cortical areas in monkeys in which they found a directional causality between two areas, but the receiver area was switching on before the sender area. So this was a clear case of anticipated synchronization, and with our theory, we could reproduce the experimental findings. In the paper I'm talking about now, which is, we did two things. One is to prove that this anticipated synchronization is a very general mechanism, or can be a general mechanism for different models in the brain, going from single neurons to population or even neural masses. Neural masses are representation of cortical areas. So we found that in all the cases, by changing the inhibitory feedback, which is the coupling, the negative coupling that was proposed, you can have a transition from delay to anticipated synchronization, or from anticipated to delay, doesn't matter, by changing the excitatory inhibitory balance. But we also found another mechanism that produced the same behavior. So we fixed the excitatory inhibitory balance, and we changed the forcing on the receiver population, this one, or this one. And we find the same transition. Even though the inhibition is fixed, we can also find with external forcing a same transition from delay to anticipation. So the question is, are these two mechanisms independent, or are more or less related? So what we find is that when we evaluate the frequency of the pulsation of the receiver, the oscillation, the frequency of the oscillation, we find that by changing the inhibition, we change the frequency, and by changing the external forcing, we also change the frequency. So it seems that the frequency of the oscillation might be the element that produce the change. Actually, when we change the frequency and see the synchronization, we can go from delay to anticipated synchronization in all the cases only by changing the frequency. So it looks like it's just a change in the receiver frequency, the mechanism that causes delay to anticipation or anticipation to delay transition to occur. And if it's that so, that this might be very easy to show, and that's what we did. If I take just two coupled Kuramoto oscillators with different frequency, nothing simpler than this, and I solve the equation, I can find that the locking state where this frequency locks is just this equation equal to 0, very, very simple. And if you expand in the first order, you have a delta omega over k, which indicates that if I have an anticipated synchronization when the detuning is negative, and I have delay synchronization when the detuning is positive. So the system with a higher frequency imposes the phase at which the two oscillator locks, and this is a very general mechanism that can explain anticipated synchronization. So just to conclude, sometimes the explanation might be simpler than expected. Thank you very much.
See, exactly like this. Okay. Okay. So, well, this is a work that has has been published this year in published this year in Nature Communication, and then I will show you the thing. But it's a collaboration of a lot of people. I mean, as you have seen, actually, in the last papers, the number of authors has been increasing. This is probably the maximum in the curve. And here, I mean, actually, the ones doing mostly this work was Aleix, as he's the first author. And then there are some other people over here. And actually, the complete names are the ones that did more work in this case. Okay. This is a collaboration of people of different institutions, but I want you to look at this one, okay? Mostly because the data that we are using is coming from there. So it's the data from Google, from Android, actually, and it's from people that has opted into something that is called location history, okay? This means around 300 million people in this database. This is the coverage all over the planet, and essentially this is assuming into the US for the mobility part. And this is assuming for the city of New York, because we are going to focus on mobility inside cities, okay? The idea of what we want to do is to generalize one thing that we did in a previous paper with Thomas and Maxime here and also Maxi, I think is over there, but here in Palma. No? So the idea is, in that case, was we wanted to determine which were the most active areas of the cities, which is what it's called hotspots, okay? So for doing this, what we were doing is, this is a curve that is called Lorentz curve, and it's typical from economy. So the idea is that in here what you have is the fraction of something, usually is economy is money, okay? In this case it's activity or mobility or whatever you want to put in here. And then in here what you have is the different elements in the system that has to divide this activity, okay? If we are talking about of cities, we are talking about small areas in the cities. It's usually around 1 square kilometer. And they are ordered by who has more. They are over here, the rich ones, and here are the poor ones, okay? So in this curve, the Gini index tells you how far this is from the diagonal and gives you an idea of inequality in the system, okay? In this case, if we are talking about mobility, this will give you an idea which are the hot spots if you decide which are the rich guys here. To determine the rich ones, what we proposed in that paper was to do a derivative here and just cut the x-axis on the point where the curve, the line cuts the thing, no? And then in this next paper, what we have done is to actually say, okay, well, we generalize this and take out these guys in the rich area and repeat the process. And then you get another threshold, repeat again the process, you get another threshold. Of course, the curve are going towards the diagonal because you are taking out the richest in every step. And in this way, you are getting kind of different levels, okay? When you do that and then you do it in cities, what you get is this. So the red one is the top hotspots, the ones that we were studying in previous analysis. And the other ones are, by color, are ordered according to which is the level that they have, okay? So, but in here you already see that there are something curious, no? So you have, this is Paris over here, and this is Los Angeles. So as you can see, the red spots are concentrated in Paris and very spread out in Los Angeles, okay? So this means that actually you have, and this is something that we have found in most of the data all over the world, you have two models of cities. One that the thing is, the activity is quite widespread, and the other one that is very, very concentrated, okay? This can be mixed with the fact that you have the mobility between these areas, and then you can think of hierarchy of this mobility. Hierarchy meaning that we have now a certain level of the different areas, and then if there is a hierarchy, the mobility between these areas should follow more or less this structure. So there is the big boss talks to the next below, and the ones below talks to the next below, no? But there is this kind of only one level difference. If you do that, you can essentially create this kind of maps of the mobility between the different levels, and with this you can define a hierarchy flow, which is how we call it a flow hierarchy, which is just a matter of how much of the mobility is happening in this diagonal. Okay, so in levels that are the same level, or one above, one below. Doing that, you can describe cities according to this, and this essentially tells you what you were seeing in the map. So the most centralized are usually the most hierarchical, and the other ones are on the other side. No? So essentially, Los Angeles is over there. Apart from classifying cities and according to the continents and things like that, the important thing here is that what we found is that there is a relation between this hierarchy in the mobility and several indicators in the city. So the first one is about transport. The hierarchical cities are usually the ones that have a best public transportation system, okay, and it is more used. It's not only that they have it, it's that they use it. that is related to the fact that there are less emission per capita in those cities too. So essentially, let's say there is less pollution in that model of cities. And also, there are parameters about health that are also related. And actually, in this case, they are related to the fact that you get faster attention, medical attention, if you are in a hierarchical city than if you are in a widespread one. Okay. So this is because there was a big discussion about the question of which is the best model of city, which is the optimal way of cities. And this has been over the table for many, many, many years, actually almost a century. And what we wanted to do with this was to kind of find some metrics, some kind of idea, and also systematize it to understand if actually there is a way to say which is the best option in the cities, or either widespread or concentrated. Okay, so that was it. Thanks.
Okay, one left. Right? So 5 more minutes and we are done. Okay, so I'm going to present this work entitled Reduction of Power Grid Fluctuations by Communication Between the Smart Devices. This is this is work mainly done by, this is part of the thesis of Eder Batista, who presented the thesis last year, myself and Pere Toral. Okay, and this was published in this International Journal of Electrical Power and Energy Systems. It is actually an engineering journal, so it was a good job. When I'm talking about the power grid, I'll be very fast. You have seen this in some other presentations already. Okay, so the power system works. You have a generation, and then you have transmission, which is high voltage power lines, distribution, which is lower voltage power lines, and the consumption. Okay, and the point is that in the electric power system you have no storage, and that's a key point, because then you have to produce exactly what is consumed at any time, and that's a difficult problem. And the balance is not trivial, because of the problem is that the consumption has a random character. So we switch on devices anytime and at any place. No? So it has to be something that controls that. And what is used to control that is actually the frequency of the power grid is an alternating current system. Okay, so it has a frequency of 50 hertz. And what happens is that when you produce more energy that is consumed, okay, the machines accelerate and the frequency increases. And otherwise, when you consume more power than it is produced, the frequency goes down. So the frequency is a proxy indicator of the balance between power and consumption, and that's what the operator of the system does. It just controls the frequency to keep it constant. And this is generally done having very fast response machines that when you need more power, they accelerate. Okay? And that's how it works typically, but this is very expensive. Okay? So these machines are very expensive, and yeah, this is a centralized way to do it. But this is okay, that's good, that's been working, we use the system all the time, but this is becoming increasingly difficult because of two reasons mainly. Well, the consumption increases and increases fluctuation, but the point is that we have to reduce the use of hydrocarbons. Okay, so we have just recently finished the international conference on climate change of the United Nations and climate change, no? That we have to reduce the emission of CO2. We don't know how quite to do that. No? And the electric system is a big part of that. So if we include renewable resources, that's good, but then the renewable resources lack this property of controlling the frequency, okay? Because you cannot accelerate the production from energy resources. Well, hydrodynamic with the hydroelectric plants you can do that, but with windmills and solar systems you cannot do that. No? So this is producing and fluctuating. Together with the fluctuations of the demand, this is a mess, and it's a difficult problem to address. That's what this talk is about. There are several possibilities to do that. One is include batteries with storage, let's say some of the extra energy produced in excess by the renewables, but that's very expensive. And another thing is what is called demand side management. And is instead of put all the control on the power plants, put some control on the users, so that we users will not switch on devices if the frequency is not good. Okay, and that is what is called dynamic demand control. And we want to study how, if we implement this massive in the power system, how will it affect the fluctuation, if the system will be stable, if it works. So we did this in a previous paper in Physical Review 2 years ago. And well, first we need a model, and what we did is use a standard model of a power plant, okay, including the primary control and secondary control. And then we suggest or propose a model, a stochastic model of demand, okay? And then you put this model into, so the stochastic model of demand in the power plant, and then you get, this is the frequency as a function of time. This is an experimental measure in one of these outlets here. Just plug and measure the frequency, and the frequency fluctuates, okay? And then our model produces something like this, after fitting 1 per meter, okay, which is pretty good. And a statistic, this is the power spectrum of this time series, and you see it reproduces the statistical properties of the fluctuation, okay? So the model is good. And then what we did was to put this dynamic demand control. So these are devices that they have to switch on. They check the frequency. If the frequency is good, they switch on. If the frequency is not good, means that there is an imbalance in production and consumption, they wait. Okay? And they will switch on at a later time. If you do this, it works. Okay? But what happens, for instance, here, you see that, so this is, so this is the original frequency, and this is with control. Okay? This works fine. But what's the problem? That if you have to switch on and you don't, then you have not done the task you were supposed to do. So you have a pending task. Then you have to recover this pending task later. When you recover the pending task, you introduce the fluctuations back again in the system in a different fashion. And what happens is that we have a threshold for recovering the pending task. It's a device that has to switch on. If the frequency is high enough, it switches on. If this threshold is low, what happens is that the devices, when they recover pending tasks, create large frequency fluctuations, which is not good. If you increase this threshold, this improves, okay, and then it looks good. And the cost is that you accumulate more pending tasks. And there is a balance, okay, and we choose this value 0.6 as a good point. So you see that the fluctuations has been reduced quite a lot, but there is a problem. So the variance is reduced, but there is a problem. If you look at the cumulative probability of having a frequency deviation larger than delta omega, the black curve is the stochastic case. Okay, so you have certain probability of have fluctuations larger than this value, but there is a cutoff more or less here, 0.2. When you include this dynamic demand control, without recovering pending task is the yellow line. That works very well. You reduce the probability of the fluctuations. But then you have to include the recovery of pending task. You see, are these lines here depending on the value of the threshold. We use the green, the gray one. You have reduced the fluctuations, the small fluctuations, but you have more probability of large frequency fluctuations. Okay? And you cannot avoid that. It's always that. Because when you introduce the dynamic demand control, you change the shape of this probability distribution, and you get these exponential tails. Okay? And these exponential tails, you always have non-negligible probability of having a large frequency deviation. So that's bad. Okay? So that's not good. So it's worse the solution almost than because this can create a problem in the system and a blackout. Okay? So the paper I'm presenting actually is a solution. We try to find out a solution for this. And the solution we came up with was to this communication enhanced DDC. And the idea here is the same thing. So the device checks the frequency. If it is good, switch on. If it is not, it waits. But we include something more. And it checks the devices in a group. A given group, it can be, let's say, your house or your neighborhood or the whole country. Okay? And if there is a device that has done the opposite action, you do it. Okay? Regardless the value of the frequency. So that you are not just trying to control the frequency, but you try to keep the energy consumption more constant. If you do this scheme, this is the stochastic case. Okay, so that's the stochastic load, the stochastic frequency. Of course, no pending task. This is the previous case I explained. So you reduce the frequency fluctuations, you reduce the variance. You see here that the frequencies are within this tolerance, but you have the problem of the peaks here. Okay? And you have the number of pending tasks, which is also stochastic. Then when we implement this control here, this now works much better. Actually, you keep the frequency all the time within the desired frequency range, and you have no peaks going outside. And as a matter of fact, if you look, because of this thing of you have the possibility to switch an action, okay, to interchange an action. This time trace looks much more similar to a stochastic than the previous one. If you look at that. So you are actually, by performing these tweaks, you are much more efficient, no? And the number of pending tasks is reduced a factor 10. So you reduce better control and reducing a factor 10. Okay, and just showing you as before, just to compare the three cases again, the probability of having a frequency fluctuation larger than a certain value, that's the stochastic case. This was the normal dynamic demand control. You have this problem for the large frequency fluctuations. And in the case of the communication enhanced dynamic demand control, actually you manage to, these two lines are for different sizes of the groups. If you have a larger group or a smaller group. So this seems to work. So that's our proposal to address the problem of including a lot of renewables and to include the control in the demand side. By the way, this could be implemented just as a final note. You can do this as a small thing, so within the house, using what is called household energy management systems, or management system central in your house that control the devices, okay? Or you can do actually, and that's our proposal in the paper, you can also do a direct device-device interaction, no? So that devices can communicate. This can be done either through internet, okay? This can be nationwide, or you can communicate through the power cable source. That this is called a power line communication. Device can check if there is another device that has done the opposite action, and they coordinate themselves in a self-organized fashion. So that's our proposal for this new power grid to come in the future. Thank you a lot.
Thank you all the speakers for keeping that